5G technology is bringing about a sea change in wireless connectivity. Its performance capabilities will serve enterprises, consumers and the public sector in a seemingly limitless way. Naturally, the 5G revolution is in meters in direct play with the massive uptake of wirelessly connected devices that require improved reliability, quality, performance and latency for communications. 5G will be connecting billions of devices, from smartphones and tablets to the Internet of Things, IoT. The Industrial IoT, IoT, will also reach its full potential through the use of 5G infrastructure by connecting factories, buildings, people, and devices. This will deliver new business opportunities and is in concert with the trend for deep analytics through machine learning and AI. Smart cities, for example, will see communications, entertainment, home management and security being provided via the internet and cloud. Yet, the real challenge is how to manage these dense deployments of connected devices to deliver the outcomes as set out in 5G. Collective experience gathered from the implementation of other connective technologies, namely Wi-Fi, comes to play as it shares a number of similar technical attributes as 5G. What have we learned from Wi-Fi? If the success and proliferation of Wi-Fi has taught the wireless industry anything, the challenges of a crowded RF spectrum, dominated by density and interference issues, cannot be repeated in 5G. The massive device adoption that 5G will result in, means the industry needs to solve the density and interference issues before they start. With 5G, the industry cannot go blindly down the same path of Wi-Fi, where adding infinitely more and coordinated access points to the wireless infrastructure reached critical mass. The process, repeated over many times, destroyed quality of service, QoS, and performance for mobile users. The upcoming shift from LTE to 5G mobile technology will become wireless' greatest challenge to date, as more 5G networks are deployed in thousands of users and devices. Jump on a network, the exponential increase of interference will severely impact performance, making the positives of the 5G spectrum erode into negatives. The 5G revolution must start with a focus on wireless network densification to reach mass adoption envisioned by all. As other widely established wireless technologies such as Wi-Fi, IEEE 802.11, have taught us in high-density applications such as inside stadiums, convention centers, MDUs, and now the home, the challenges of addressing density and the associated interference issues are enormous. The biggest challenges operating in dense environment are compounded in unlicensed spectrums and negatively impact the user experiences. As Wi-Fi has taught us, it doesn't matter how fast wireless is, once the flood of users, devices and video feeds are crowding the same wireless radio, and the realities of addressing real-world interference issues. Since the advertised numbers on the box are never delivered, 3 ways to improve performance in dense environments: increased speed of wireless connection, association rate, increased density of uncoordinated radios, i.e. multi-single channel APs, negate speed of connection. IEEE report, increase channel density, only effective path forward in density. The common engineering answer had been to increase bandwidth of individual, uncoordinated radios by implementing complex techniques, MIMO, UMIMO. This increases channel width. Another way is by implementing high-density modulation, increased QAM, but, as found with Wi-Fi, the techniques struggle to deliver promised performance outside of a Faraday chamber. Association rates rarely approach the on-the-box marketing numbers offered by vendors. In fact, the results are worse, similar to trying to increase the speed limit on a congested, single-lane road. Network engineers, now forced to work with legacy architectures, take to increasing the density of uncoordinated radios in attempts to offer more capacity. The results, particularly in the challenging unlicensed spectrum occupied by Wi-Fi, have been poor quality of service and frustrating user experience. This happens regardless of the network, radio resource management techniques, AI algorithms, or marginal gains techniques used. For 5G, wireless network densification, building on a traditional single-channel architecture, requires more radios, adding capital expense and operational expense and allowing minimal spectrum reuse. Scaling to meet the dream of wireless everywhere for everyone simply can't be done. Deploying multiple access points in close proximity is really about delivering more channel capacity in a given area. Increasing channel density in a given area is the holy grail, enabling better performance to be delivered to where it's needed most, the end user. However, as we have learned in Wi-Fi, increasing channel density requires addressing interference, specifically co-channel and adjunct channel interference, CCI, ACI. In Wi-Fi, defeating CCI and ACI has led to a raft of innovations, from complex network designs where access points are physically deployed under seats in stadia adding $1,000 as per cable pole, to advanced beamforming techniques which attempt to focus, transmit energy to the end user, to controller-based radio resource management algorithms which attempt to centrally manage the dynamic spectrum, and now, multi-access point mesh solutions. The list goes on and on. While some of these techniques deliver marginal gains, they continue to struggle to address the physics of interference. Delivering capacity in dense environments requires increasing channel density and network. Unlocking better frequency reuse across deployments requires the delivery of multiple channels in a coverage area. The path to a better future with 5G and its wireless everywhere approach requires RF optimization and engineering better frequency reuse. It is achieved by allowing for the use of multiple, concurrent channels in a given location, offering true wireless network densification. The answer for 5G is to utilize a multi-channel single radio, MCSR, architecture. This coordinates multiple, concurrent channels from a single, standards-compliant radio. MCSR mitigates the impacts of ACI and CCI while extracting the maximum usable capacity from limited spectrum. A better answer with the massive influx of wireless devices and connectivity everywhere. The very foundation of 5G must be based on efficient spectrum utilization, and efficient spectrum utilization is about packing more and more usable channels of capacity in a given area. Building an effective 5G standard simply must include advanced radio architectures which deliver multiple, concurrent channels from a single radio. 5G must both coexist with established technologies such as Wi-Fi, and compete to provide a compelling migration to the new platform. As a result, network operators and vendors alike must focus on optimizing spectrum utilization to deliver the compelling user experience we deserve. We all, as in the wireless industry, need to do better. In the real world of wireless, there are precious few greenfield deployments, and network operators must prepare for the cold hard realities of density and interference.